Okay, so welcome to today's video tutorial. Today's video is going to be a little bit more technical than ones that we've done in the past. Typically we're doing stuff on how to use ops and looking over various flags and so forth. This one is going to be a little bit more based upon, some technical implementations of a feature that we recently introduced. So as the title suggests, it is about UMCG, user mode concurrency groups. So this is a feature that came out of Google. It's a feature that Google's been trying to upstream to the mainline Linux kernel for quite a few years now. Hasn't ever really gotten merged. This is one of those things that larger companies like Google that have large and many systems to deal with. It's something that benefits them quite a bit. Your average desktop Linux user maybe not. So that's part of the contention. But it really kind of gets at the root of it is that scheduling is not a solved problem. And so what is scheduling? Scheduling is basically you have the operating system. Let's say we're talking about Linux. You have the operating system and you have all these different programs running on it, right? And so the operating system, one of its jobs is to figure out what to run when. If you have one CPU, and for the sake of this argument, let's just say it's single threaded or whatever. If you have one CPU, the kernel needs to figure out how much time and when to give some processing time to the various programs that are running, because you have hundreds of processes, right? So Unikernel land, that's a little bit different, but it still does scheduling, because even though we have one process, we still have many threads in many cases, right? So scheduling is a concern. And a lot of organizations, Google, Microsoft, lots of people have observed that while a context switch might be expensive, scheduling itself can be super expensive, to the extent that Google has written not one, but like many different user level scheduling frameworks to get around this problem. So anyways, we thought it was really cool, and we think everybody else should use it too. At least have access to it, let's say. And so we went ahead and ported it. The end result is that you can design, your applications to kind of control the scheduling in a much more tighter manner than you might be able to do with normal threading. So let's just kind of take a look and dive into threads real quick. If you've done any threading work on Linux, this will look familiar to you. This is just classic P threads, where we spawn a couple of threads with create, and then we run thread 2. Once they've completed, we join, and then we quit. So if you're using like Go, Java, Rust, pretty much any compiled language out there, you obviously have access to threads, and they expose them in different manners, which is all great. But if you're using a language like Ruby, JavaScript, Python, PHP, any of the interpreted languages, you probably don't have access to threads. And if you want to scale, you probably have to scale out horizontally versus vertically. So vertically is like throw more threads and RAM at the problem. Horizontally is spin up a load balancer and then spin up so many instances behind it. Now, why is that a problem? Well, the problem is because a lot of these interpreted languages are designed to be very easy to use. But that functionality that makes it super easy to use makes it really, really hard to make it easy to use with threads. And let me just show you what I mean real quick. So if we pop over into the terminal, we pull up Ruby, Ruby's still used by a lot of companies in the Valley, for instance. So like Stripe runs on Ruby, Shopify is Ruby, right? There's a lot of people using Ruby still. And let's say we have a class named dog, right? So we can do like dog.new, right? and maybe dog can do a wolf or whatever. So it's really easy to use. However, look at this. We can just do this, or we can just say the entire class. You know what? We're gonna cast it to a string. And so now, what used to be this, this could be a massive freaking multi-thousand line class. Now it's just a string. And so this highlights the issue that threading and interpreted languages really have, and that is because when you have threads, they share the heap, but all this stuff goes onto the heap. And so what are you going to do? Start putting like mutexes on everything? No, it doesn't really work that way. And so there's other solutions that people have been designing. So like V8 isolates is one method. And so in JavaScript land, for instance, if you have a JavaScript worker, what's happening is when you spawn a new JavaScript worker, is you actually spawn a new V8 isolate context, and so that spins up, and that's like a completely different VM that you're running there, a JavaScript VM, and so like the variables that you're working with there, for it to talk to your other non-worker thread, it actually has to use message passing. Because it's you don't want to stomp on these variables, right? So it's a very different issue. Anyways, it makes threading hard with interpreted languages, and so people kind of go out of their way to do other things. All right, so back to threading in languages that can actually use it. The traditional way we use threads, right? The traditional way is, if we go all the way back to, say, like the 90s, we have these things called condition variables and mutexes. And essentially, mutex, which you might be familiar with, all it does is prevent other data from accessing, a variable when maybe another thread is trying to use it. And the condition variable will allow you to basically wait on access to it. So back in, say, 2000, I don't know when it was, 2002, 2003, somewhere around that time, we got Futexes, and then later on we got robust Futexes. And basically what this does is it's short for fast user space mutex. And essentially it says, hey, let the user space deal with the mutex versus, having to go back to the kernel each time and get access, because it's expensive. So this is like one of the reasons why, if you go back to, early 2000s, late 90s, that sort of thing, that was one of the reasons why people said threading was slow at the time. This was like a real complaint that people had. Totally invalid today, right? But back then, people would say this. So that's where Futexes come in. So pretty much everything that you use on Linux today that uses threading, it's going to be doing Futexes. You can see this with set robust list. There's get robust list, and then obviously this Futex call. This output I just got from running like strace. It's really straightforward. Everything uses this. In this article, we kind of go through all the different languages, and we go through various operating systems to see how they're implemented. I mentioned that JavaScript doesn't actually have threading, but in reality, what happens is, say Node.js actually isn't JavaScript, right? So Node.js is a runtime that runs JavaScript. And so while your JavaScript doesn't have access to threads, Node.js definitely is using threads. And in particular, it's using these two libraries, V8 and libuv. Both of those definitely have access to multi-threading. So this feature, UMCG, if I was going to throw it into some JavaScript using program, I would be looking at places like V8 and libuv to plug it in. We go over to Rust. This is how you would do like a simple threading in Rust. I point this out. Some people might get confused. They're like, well, why are you even pointing this out? And the reality is that languages they run on different hardware, right? But B, they also run on different operating systems. So like you can run Rust on Windows and Mac and Linux and like all over the place. I mean, they've got like weird platforms that they support, right? So not every operating system has the same sort of calls, and we'll show you, why that is. Um, just to point out, Mac OS. So I'm on a Mac right now, right? So if we rewind to the x86 Mac OS period, a handful of years ago, call it like, I don't know what, pre-COVID or whatever. During that time, Mac OS actually had really slow mutexes. This was something that people like Garrett Demore and others would point out, kind of trash talk on, right? So, anyways, it seems that Cupertino did fix this. Now they have the micro lock wait and micro lock wait calls, and so now that works as expected. This is your GCD implementation of threading, and this is the strace equivalent that we would use on Mac OS with ktrace, just to kind of show you the stuff. And then, FreeBSD obviously has this UMTX op with wake and wait as well. So that brings us to, what is this feature? So this guy, if you look him up, Paul Turner, he works at Google, or at least did. I like this quote that he has. It's context switching lacks the context. And so what he's saying here is that when you make a context switch, generally speaking, the operating system kernel doesn't really know what your program is doing. Like, yes, it knows the syscalls that it's making. Yes, it knows some of this other stuff, but it doesn't know the logic of like what's going on. You, the developer, kind of understand the logic because you wrote the program, or at least you're using it, right? So his thing here is like saying that the program generally has a better idea of what should be executing at any given time versus the kernel, and he's not wrong. The whole this is analogous to hypervisor and hypervisor guests as well. So that's also like its own like scheduling conundrum, because the hypervisor host, again, also doesn't really know quite really what the guest is up to. Not in a way that makes optimal scheduling anyways. So this idea user mode control groups, basically, and there's a couple parts to this. Basically, what it does is it just shifts some of these scheduling decisions down to user space, to where the user space can kind of basically say, hey, run this operation or don't run this operation. And when coupled with lightweight threads, what you get is a much faster experience, and you can do a lot of other things that you wouldn't be able to do before. So some analogies. Big on analogies in this episode. So if you've ever used Go, there's this concept of Go routines, right? A lot of people really like it. It's an implementation of green threading. You also have Java virtual threads, which is pretty brand new in Java land. I think that's just going to blow up and actually kind of make the JVM, usable again. So there's that. There's a couple of these concepts out there, and basically it's the same sort of concept, but now you can use it like in any language, because we now have this syscall to kind of implement this in. So I could see like a libvuv, sprinting up around this, and then you have like all the different JavaScript runtimes and Python runtimes and so forth start to use it. I could totally see that happening. This is going to allow all sorts of interesting, software be made in a much more scalable format. That's so we're trying to say this is a big deal, right? All right. So what exactly is the bulk of this? So essentially, everything really relies on this is called UMCG control, and we have a few arguments that we can pass. But basically, yeah. So here, basically, the first thing that we would do is register a server, and then we register a worker, And so when you spawn, spawn this worker thread, we can register it there. We can wait, or we can wait for that thread, and then after our thread is finished, we can clean it up by unregistering it from our server. So these are like the base operations that allow you to work with this. Now, again, I think, more than likely in the future, you would probably access all of this from a library instead. And then maybe there would be like, language bindings on top of that library. It's not common for people to just issue their own syscalls anymore. Generally speaking, libc likes to broker a lot of that. It's kind of been slipping through the cracks. I mentioned we did the BSD pledge and unveil. Obviously, that's not on Linux, so that's why we have that in npm and stuff now. Yeah, so let's show you the code real quick. So I'm actually going to show you the let's show you the test if I can. Oh, okay. So test runtime, not source runtime. So I'll show you this manifest real quick. If you ever used ops before, you might have ran across these manifests before. This is basically a representation of both the file system and metadata, and we kind of stuff it into this tuple space that we have. You don't craft these by hand unless you're doing Nanos development. Ops auto-generates all this, and sometimes it auto-generates these like massive ones. So it's definitely not something you craft by hand, but for this example, we're going to look at it. Anyways, down here is this arguments. So for this test, we're going to start off with -c for a condition variable. And what I'm going to do is show you how fast we can kind of switch between a newly spawned thread and the thread that we were, working from, the parent one. And so we're gonna go over 3 use cases. One's condition variable, one's Futex, and then one is the UMCG. And just so you can kind of see for yourself what this looks like. And then we basically do make, and we give it a target of UMCG, and then run. Each of these takes about 10 seconds. And that's, we give it some time to actually get a good idea of what it is. So in this one, we did like 400,000 some odd cycles a second. Okay, not bad. Now let's edit this. We're going to go from -c to -f for Futex. All right, let's run it again. So now you can see we're doing Futex versus the other one, which I guess was up there. All right, so we had 400,000, right? All right, so Futex, this bumps us up to about 500,000, like right under 500,000. That ain't bad, right? So let's go ahead, let's go down here. And I think it's -u for UMCG. Now we run this guy, all right? Yeah, so now it says UMCG. And so again, we're just kind of flipping back and forth between these 2 threads. This is a pretty naive benchmark, but it does give us an idea of, what we can kind of expect. Now here you can see that this jumped up quite a bit. Now we're doing 670,000. So I was doing the same test like earlier, and I mean, it was like right under 700,000 at one point. So as you can see, this is a pretty large difference. This isn't like a small difference. This is quite considerable. And so it just kind of shows you that there's definitely a lot of promise here. Obviously, we need better, benchmarks here, and obviously, being able to showcase some software that actually makes use of this would be great. But I think this gives you an idea of where this is going and how powerful of a feature this is, and how well this really fits into unikernel land. Anyways, so I hope that wasn't too much. I will talk to you all in the next video. Bye.